So now what we're going to look at is what happens when we can't get the same base on both sides. And in cases like that, we're going to use logarithms in order to solve. And what we're going to do in order to solve is first off isolate the exponential expression on one side of the equation. And then we're going to use either the common log when we have base 10 or the natural log in any other situation. So for instance, if we have ln of b to the x, the property of log will allow us to move that x to the front and make it easier to solve. If it's ln and e, then ln and e are going to cancel out and we're just going to leave with the x itself. If it's log and it's base 10, then the log and base 10 themselves will cancel out as well, leaving us with just the variable that we can solve for. So let's look at one example here that goes 5 raised to the x minus 3 equals 137. Now this is certainly a situation where we can't get the same base on both sides. And so what I'm going to do in order to solve is I'm going to use the ln, the natural log. I'm going to take the natural log and put it on both sides. Now if I put the natural log on both sides, the property of logarithm tells me I can take what's inside as the power and move it out to the front of the logarithm. That would change this into x minus 3 times ln 5 equals ln of 137. Okay, now that's helping us out because now the x is down here rather than up there. In order to solve, I'm going to go ahead and distribute this ln of 5 into the parentheses. That's going to make it x ln of 5 minus 3 ln of 5 equals ln 137. Now this ln and all the numbers, just treat them like you would any number. We can move them around from one side to the other side of the equation. So what I'm going to do is I'm going to add 3 ln 5 to both sides. So that'll give me x ln 5 equals ln 137 plus 3 ln 5. Okay, so again, the whole goal here is just to move everything over, leaving just x by itself to solve for. And now we're just left with x and the ln 5 together here. The way I can move that ln 5 away from the x is to divide both sides by ln 5. Okay, and that will go ahead and get rid of it here. And so we're going to have x is equal to ln 137 plus 3 ln 5 all over ln 5. A fairly long solution, but altogether that's going to be the solution for x here. So here's another situation to look at. 40e to the 0.6x minus 3 equals 237. The very first thing we want to do is isolate the exponential part. So the way we do that is we're first going to take the 3 and add that over. So we're going to get 40e to 0.6x is equal to 240. We can then divide both sides by 40 because we're just trying to get e to the power situated here by itself. So divide by 40, 240 divided by 40 is 6. Okay, and like the last example, I'm going to use the natural log on both sides. Okay, and if I take the natural log, the ln on both sides, think about what the ln actually stands for. ln stands for log base e. So I can change that to log base e of e to the 0.6 equals log base e of 6. Okay, in the property of log, we can take this thing and move it out to the front. So that's going to be 0.6x log base e of e. And so log base e and e, those things are going to cancel each other out basically. So we're going to have just the 0.6x and the log base e ln, we'll call it ln of 6. And so now x is pretty much by itself at this point. We got rid of the e, leaving us just that part. We can divide out both sides by 0.6. And so x is going to equal to ln of 6 divided by 0.6. Okay, now on this example we got to look at a few different things. We have e to the 2x minus 4e to the x plus 3 equal to 0. The weird thing about this one is you have two different e terms, and they're not like terms. So how are we going to go about solving for x when we have it up above in two different e terms? Well, this thing, it kind of almost fits in the form of a trinomial, almost kind of like a quadratic equation. So what I'm going to do is I'm going to make some kind of substitution in order to make this thing a little bit easier to work with. So what am I going to do? I'm going to take a letter, we'll just call the letter u, use the letter u, and we're going to let u stand in for e to the x. That also means that u to the second power would be e to the 2x. So I can put a letter u in there instead to take care of this whole e to the x business that's going on here. So if I do that, if I make that substitution, this will change to be u to the second power minus 4u plus 3 is equal to 0. And so now it looks much like a quadratic equation, and really we could even try to factor it to see if it would work. So if you'd like to think about this thing for a second and think about how it would factor, you could pause the video, and in just a second I'll go ahead and show how this one will factor. This one is going to factor into u minus 3, u minus 1 is equal to 0. So now what we can do is take each of these factors, set each equal to 0. So we're going to have u is equal to 3 and u is equal to 1. But that's not quite done. We still need to solve for the original variable that we started with, for x. The whole purpose of using u was just to make it a little bit easier to work with. So we had up above that u is e to the x. So each of these u's, I'm going to change that to be e to the x. E to the x equals 3. E to the x equals 1. And so like before, I'll put the ln on both sides. And keep in mind again that ln is log base e. And when you have log base e, then if you have e to the x, then it's going to cancel out the e, and the e, both are going to cancel, log base e and e. So that'll solve for x. In other words, x is equal to ln 3 and x is equal to ln 1. So by putting the ln on both sides, that's there so that I can cancel out the e, leaving just the x on both equations.